Hi everyone, and welcome back for another exciting week of research and evaluation. Today's topic is going to be sampling. To get started, I'm going to talk through some important terms that you'll need to know as we talk about sampling. One is the population. The population is some group that you're interested in, and this is specified by theory, so it could be anything. For example, if you're interested in understanding attitudes about the death penalty in the United States, your population would likely be all adult citizens in the United States. So all people in the United States who are likely to have some kind of attitude about the death penalty. But as I've mentioned in other lectures, a population can be anything. If you're interested in understanding the migratory behavior of birds, your population would be birds. An element is a single member of a population that can be selected into your sample. So going back to our attitudes about the death penalty example, an element in our sample would be a single adult US citizen. So our population of interest are all adult citizens in the United States, and an element would be one of those, so one single person. A sampling frame refers to all elements that can practically be selected into a sample. So let's say that in order to do this study, we're going to send out a mail survey to randomly selected addresses in the United States. In this case, our sampling frame, so people who have a chance of being selected into the survey, would be all people who live in the United States and have correctly listed addresses. So for example, our sampling frame would not cover some people who are in our population, such as people who are homeless. So there's the population, and then the sampling frame is always a narrower group within that. The best kind of sample, and the one that we're going to talk most about today, is a probability sample. A probability sample is a sample for which every element has a known chance of being selected from the population. In other words, you know all the members of your population or sampling frame, and you know the chances that each of those members will be selected into your sample. And as we'll talk about, this is really important when it comes to generalizing from the sample to the population that you're interested in. But for now, we'll leave it at this definition, which is that a probability sample is a sample for which the chances of being selected into that sample are known for all elements. An example of a probability sample here would be a questionnaire that's mailed to randomly selected addresses. So we have our sampling frame, which is all addresses that we have listed for the United States. And if we randomly select addresses from that, every address on our list has the same chance of being selected into our sample. So we have a probability sample of addresses that we're mailing this questionnaire to. In using samples, our goal is often to find out population parameters. And population parameters are the true values of some variables in the larger population. As an example here, we might be interested in learning the percent of United States citizens who support the death penalty. This would be the true number in the population that you would find if you were to ask every single person in the population what they think about the death penalty. But because we can't actually ask every single person in the population what they think of the death penalty, we're going to be finding a sample statistic instead. And the sample statistic is going to be an estimate of that population value that's based on our sample. So as an example here, if we were to do this mail survey, get 1,000 responses, the percent of those 1,000 responses who say they support the death penalty would be a sample statistic. We'd be using that sample statistic to try to estimate the population parameter, which would be the true value of death penalty support in the population. So why sample things? And why do this lecture right now? The main reason is that it's often impossible or impractical to study whole populations. Whatever your study is, there's some population that you're interested in. But most of the time, except in very rare instances, it's simply not practical to reach every member of that population. So in our example on the last slide, you might be interested in attitudes about the death penalty among people who live in the United States, but you can't actually ask every single person who lives in the United States what they think about the death penalty. You might be interested in the migratory patterns of birds, but you can't look at every single bird. You might be interested in police use of force, but you can't look at every single police officer. So because of that, we use sample statistics to make inferences about the true values of things in the population. And we do that by sampling elements from a population to use in our studies. So today's lecture is going to be all about sampling, how we do it, the different kinds, and what to look out for. So once you have a sample, you again use it to generalize to a population. And we've seen the word generalized before, and what generalized means is that you're looking at data from your smaller sample and using it to make some sort of assumption or educated guess about what's actually going on in the population. In order to do this, your sample needs to have a couple of qualities. One is that it should be representative. A representative sample is one in which the sample statistics match the population parameters. For example, if your population is 50% male, 50% female, a representative sample should also be around 50% male and 50% female. If your population has an average age of 38, your sample should have an average age of around 38. And note that I'm not saying that it needs to have the exact same statistics as the parameters in order to be representative, but it should be close. And also, in order to generalize to a population, you need to account for something called sampling error. So if you were to take a sample from a population that's 50% male and 50% female, there's a good chance that your sample is going to come out 45-55. This doesn't mean that there's anything wrong with your sample. It just means that you happen to draw a few more men than women, or vice versa. So in order to make inferences about a population from a sample, you need some way to account for those random errors. So let's say that you're trying to learn about the death penalty, you take your sample of 1,000, and you find that 55% of the people in your sample support the death penalty. How can you be sure that 55 is the right number and that the true population parameter isn't really 50%? Well, you can't be sure, but we're going to talk about how we address those differences that can occur when you take a sample from a population. Before we get into that, though, I'm just going to talk about a couple of different kinds of probability samples. The gold standard sample, and the one that all sorts of statistical inferences are based on, is something called a simple random sample. And in a simple random sample, every element has an equal chance of being selected into the sample. And there are two steps to create a simple random sample. One is to list every element in your sampling frame. The second is to use some sort of random device to select as many elements as you need. So let's break that down. Let's say that you do want to take a random sample of addresses in the United States to mail a survey to. Your first step would be to list out every valid address in the United States. That would be a pretty long list, but you could do it. So you list out every address in the United States. You've now listed out every element in your sampling frame. The next step would be to use some sort of random device to select as many elements as you need. Let's say we want to take a sample of 1,000 people. One way to do that might be to use a random number generator and only sample the addresses that the random number generator tells you to sample based on their place in the list. So you get a random number of 8, and you're going to sample the 8th address on your list. There are other examples of simple random samples that you see in the real world. So one is jury selection. And jury selection is typically done using a simple random sample of registered voters. So all the registered voters are listed out, and then some sort of random device, often a random number or just a computer that can randomize things, will pick out members of that list as a sample. But another example of a simple random sample would be something like bingo, where all the elements in your sampling frame are all the balls with the numbers on them, and your random device is that big ball thing that you pull the smaller bingo balls out of and then yell them out for all the people to punch their cards with. So in either case, you have a sampling frame in which you're able to list every element in the sampling frame, and then using some sort of random device to select as many elements as you need. And in all of these cases, every element has the same chances of being selected into the sample as every other element. So when you do bingo, you don't have a greater chance of getting any one ball than any other ball in the bingo machine thing. For jury selection, as long as you're a registered voter and you're on the list, you don't have any greater or lesser chance than anybody else who's on that list. So these are all simple random samples. An advantage to simple random samples is that they're always representative. In other words, you can always expect that the population parameters will be more or less reflected in the sample statistics, at least accounting for that sampling error that we talked about. A disadvantage to these, though, is that it's often difficult or costly to do them in practice. So in reality, actually listing out every single address in the United States and sending a mail survey to 1,000 of them would be a ton of work. And so a lot of the time we don't actually use simple random samples simply because there's too much of a burden in terms of the effort or cost that needs to go in. Because of that, there are other probability samples that are often used in research. One example of this is something called stratified random sampling. In stratified random sampling, you're going to do the same first step, which is to list all members of a population, but then you're going to divide them into subgroups. So for example, you might be interested in getting a sample that has multiple groups that are divided up by something like participant race. Maybe you want to get attitudes about the death penalty among people who are white, people who are black, people who are Asian, and people who are of other races as well. If you were to just do a simple random sample, white people would be way overrepresented because of their overall representation in the population. So if you wanted to get enough data from each group to do something with it, you might want to divide into subgroups first, and then simple random sample from each of those subgroups. And doing that, you could get as many people as you wanted from each group that you could include in your sample overall. So an advantage of this is that it's also representative. You know that within each group that you're sampling, you have a representative sample, and it's really useful when you're looking at a small subgroup. So for example, if you were looking at attitudes about the death penalty in the United States by race, if you wanted to understand what Native Americans think about the death penalty, you'd have only a very small number who would be included in a simple random sample, because there's only a relatively small proportion of Native Americans in the United States. But if you were to do stratified random sampling, you could break everybody up into groups and then sample as many people from that group as you wanted in order to represent their views in your sample. A disadvantage, on the other hand, is that it requires knowledge about the true size of each subgroup if you want to then adjust it to be population representative. So if you're looking at attitudes by race in the United States, if you wanted to get population level estimates, so for example, if you wanted to use your sample to then find out the true level of death penalty support among everybody in the United States, you'd have to adjust some of your estimates based on the size of the subgroups. And I'm not going to go into survey weighting or anything like that here, but one disadvantage is that if you do this stratified random sampling and you don't know the true size of each population subgroups, some of your broader estimates can get a little bit wonky. Another kind of probability sample that you see every once in a while is something called systematic sampling. For this one, we're also going to list all members of a population. But here, instead of doing a simple random sample, we're then going to sample every nth member. In other words, every other member, every third member, every 10th member, and so on. And this is a strategy that is not used very often because of how easy it is to randomize things with computers these days. But for example, if you didn't have a computer to use as a random number generator and you wanted to, say, sample people in a phone book, you might just go through and do every 10th person on the list, for example. Something to look out for. Oh yeah, so an advantage is that it's easier than SRS, especially if you don't have some sort of random number generator. But a disadvantage is something called periodicity. And periodicity refers to the sort of ups and downs that things do in different periods of time or intervals. As an example, if you wanted to find out the average temperature in your town, and you only check the temperature every 12 months, you would not get a very good estimate of the temperature over the year, because every 12 months, it's going to be September again, and the temperature is going to be about the same in September, but different from other months in the year. So you want to look out for that if you ever see systematic sampling. We're going to talk about one final kind of probability sample here that's used really, really commonly in poll and survey research. And this is something called multi-stage cluster sampling. In order to do this kind of sampling, The population is divided into groups or clusters, and a simple random sample is taken of those. Of the sampled clusters, each of those is then broken down into smaller clusters, and a simple random sample is taken of those. And you finally repeat until you're at the level that you want for the desired element. And I'm going to show an example of this on the next slide, which I think it'll be a little bit easier to understand. But quickly, an advantage is that it saves time and money because you're narrowing down the list of things that you're looking at each time. A disadvantage is that it increases sampling error. So your estimates are likely to be less close to the true population value than they would be otherwise, but not necessarily in a way that's biased, just they're going to be a little bit more off. So an example of multi-stage cluster sampling would be to start with US counties. You could list out every county in the United States and then pick 50 of those. So that's less of a heavy lift than, say, listing out every address because there are only so many counties. So now that we have sampled 50 US counties, we could then sample 100 cities and towns from those counties. So with each stage, we're narrowing it down, but each time we're doing a simple random sample, so we're keeping our representative sample here. Then you could sample 200 city blocks from each of the cities you sampled. So with each of these steps, we're narrowing it down and narrowing it down some more. And finally, you might sample 1,000 residents of those city blocks. So with each step, we have another random sample, which means that we're keeping those good qualities of random samples that we have, but we're saving time and money by narrowing down the list of elements that we need to consider each time. And here we'd end up with a probability sample of 1,000 US residents that would not require us to list out every single address in the United States before we started. So I've mentioned sampling error a couple of times, and now I'm going to dig in deeper to what it really means. Sampling error refers to differences between populations and samples that arise simply from random chance. And I'm going to go through an example in a moment, but before I do, I'll note that there tends to be less sampling error when you have large samples and also when you have homogeneous populations, or populations in which most of the members are pretty similar to one another. So, the example. Let's imagine a bowl of 10,000 M&Ms, and 50% of those M&Ms are red, and all the M&Ms are mixed up together. So it's just a big bowl of M&Ms, 50% of which are red. This is a population that we could take a sample from. Imagine that you then take a handful of M&Ms. Look at it in your hand. You would expect that around 50% of those M&Ms would be red, but not exactly. Right? So maybe if you pull out 10 M&Ms from that big bowl, you're going to find that 4 of them are red. That would be 40% of your sample. But it wouldn't be hugely shocking, right, to find 4 red M&Ms instead of 5 red M&Ms. And that's sampling error. When you take a sample, the statistics you see might differ from the population parameters just by chance. You could imagine then that you take out another handful of M&Ms. This time, you have 10 M&Ms again, but 6 of them are red. That would just be by random chance, and it wouldn't mean there was anything wrong with your sampling method. It just means that you happen to pull out more red M&Ms this time. So the sample statistic you have of 60% red M&Ms doesn't exactly match the population parameter, which is 50% red M&Ms. Let's also talk about sample size. Imagine that you take that big bowl of 10,000 M&Ms now, and you dump 5,000 of them into another bowl. If you were to look at that new bowl of 5,000 M&Ms, you'd expect that around 50% of them would be red, and that the number would be really, really close to 50%. The reason is that it's extremely unlikely that you would just happen to dump a lot more red M&Ms into this big bowl by chance. And it's the case, sort of a statistical fact, if you will, that the larger your sample, the closer your statistics are to the population on average. We also talked about homogeneous populations. So now imagine that that big bowl of M&Ms is 99% red instead of 50% red. This time, whether you take a handful or dump a big bowl of M&Ms from this new bowl, you'd expect to see around 99% red M&Ms in your hand. It might be 100%, it might be a little less, but chances are that in this bowl of M&Ms that's almost completely red M&Ms, every sample you take is going to be pretty much full of red M&Ms. And so this is the idea that the more homogeneous your population is, or the more similar all the different members are to each other, the more likely it is that you're going to have a sample that's similar to the population. And all of this feeds into something called probability theory. In this class, I only talk about probability theory a little bit. If you took stats with me, or if you ever take stats with me, you'll have to hear about it a whole lot more. But here I'm just going to describe it in a nutshell. So probability theory says that different samples will have different sample statistics, thanks to sampling error. In other words, if you take one handful of M&Ms from the big bowl, 5 of them might be red, 6 of them might be red, 4 of them might be red, 2 of them might be red, just by chance, just because you happen to grab more or less red M&Ms in that handful. So different samples have different sample statistics. You're more likely to get a sample statistic that's close to the population parameter than one that's far away. So imagine that you pulled out a sample of M&Ms from that bowl and there were no red M&Ms at all. That would be a little surprising since half the bowl is made of red M&Ms. It would be less surprising if you got about half of red M&Ms in your hand. So it's more likely that your sample is going to look like your population than that it's going to not look like your population. So in other words, your sample statistics tend to look like your population parameters, except by chance. But you're most likely to get a sample statistic that's close to the population parameter when the sample is large. So if you pull out 10 M&Ms versus 100 M&Ms, it's more likely that you're going to see different numbers of red M&Ms in your 10 M&M sample than it is in your 100 M&M sample. So the bigger your sample, the more likely it is that your sample is going to resemble your population. Or in other words, that the sample statistics are going to be close to the population parameters that you're trying to estimate. It's also more likely to get sample statistics that are close to the population parameters when the population is homogeneous. So with this one, I use the example of the M&Ms on the last slide. Another example would be if you were surveying college students versus a general population sample. It's more likely that if you surveyed college students who are similar to each other, often in terms of age and level of education and background, than if you were to sample a general population sample. So just anybody out there, with any sort of age, education level or background. So estimates from the college student sample would most likely be closer to the true parameters for the population of college students then estimates from the general population sample would be to the true population parameters for just that general population you're looking at. The nice thing about this is that you can estimate how far off a sample statistic is likely to be from the population parameter based on those two characteristics, the size of the sample and the homogeneity of the population. In other words, any sample you take, you can get a pretty good sense for how close it's likely to be to what you're actually looking for. The problem in sampling, though, is that you only ever get to see one sample. So you can imagine reaching into that bowl full of M&Ms, pulling out one handful after another and after another and after another, and seeing the variation in the number of red M&Ms that you get with each handful. In reality, though, if you're doing research, you only get one handful of M&Ms to look at, and then you have to use that handful to try to estimate the true number of M&Ms that are red in the bowl, with less M&Ms usually. But the issue is that you don't actually get to see the variation caused by sampling error. You get one sample and you have to use that sample to try to estimate the parameter in the population. But because of those qualities of sampling that we just talked about, you can make an educated guess about how close your sample statistic is to the population parameter based on the sample size and the homogeneity of the sample. So if your sample is bigger, you can be more certain that your sample statistic is close to your population parameter. And if your sample is more homogeneous, so if the members of your sample are more similar to each other, you can also generally get a better idea that your sample resembles your population, and that your sample statistic is likely to be close to your population parameter. These two things are summarized in something called a confidence interval. And in this class, again, I don't make you calculate them, but it's good to know what they are because they do pop up pretty often. And a confidence interval is just defined as some range that includes a population parameter, such as a mean or a proportion, at some level of certainty. So for example, you might see something somewhere that says we can be 95% certain that the true percentage of M&Ms in the bowl is between 45% and 50%. So that would be something that you could estimate using a sample. Even more common, though, it would be something that you see in polling. And what a margin of error is that confidence interval around the poll estimate. So if you see a poll that says, this poll estimates that 55% of people in the United States support the death penalty with a plus or minus 3% margin of error, that means that the confidence interval around that estimate goes out to 3 percentage points on either side. And basically, you can be certain that between 52% and 58% of people support the death penalty in the United States. So just to sum up here, confidence intervals and margin of error are essentially buffer zones around the estimates that you get from your sample, and they tell you what the range is that is likely to include the population parameter that you're interested in. The bigger your sample is, the narrower that range is likely to be, because the more certain you can be that your sample is close to the population. The more similar members of the sample are to each other, the narrower that range is likely to be, because again, you can be more sure that your sample resembles the population. So that was probability samples. And probability samples, again, are useful for getting estimates about population values, because we can use probability theory to get a really good sense for how close our estimates are likely to be to the true population values. Non-probability samples do not have that wonderful quality, but they're also really common in research. So I'm going to talk about them as well, and talk about what to look out for if you ever see a non-probability sample. So a non-probability sample is a sample in which every element in the population or in the sampling frame does not have a known chance of selection. In other words, as you take your sample, you actually have no idea how likely it is that one member of the population is going to be included in the sample relative to some other member of the population. And it could be that some members of the population are excluded entirely from your sample, and you'd have no idea. The use of non-probability samples often results in something called sampling bias, which is when your sample is not representative of the population because of some problem with the sampling process. So let's say, for example, that you want to measure attitudes about death penalty in the United States. And to do this, you go to your local Republican group and ask everybody whether they support the death penalty. Chances are, responses from this group are going to show a pretty high level of death penalty support, because Republicans tend to support the death penalty more than Democrats do. If you were to just do this one sample, though, and come away saying, well, 90% of people support the death penalty, you'd have a problem, because your sampling process didn't include a lot of members of the population, such as independents and Democrats and people who are apolitical, who may also have attitudes about the death penalty, and who are likely to have attitudes that are different from the members of your sample. It's also important to note that a difference between sampling error and sampling bias is that sampling error happens all the time and is totally fine. It's just differences between a sample and a population that occur by random chance. Sampling bias is a bad thing and happens when your sampling process isn't very good. And sampling bias refers to differences between your sample and your population that occur because you are not including important members of your sample. Because of this, non-probability samples are really bad for understanding the prevalence of attitudes or behaviors in the population. So thinking about that last example, if you wanted to understand the true prevalence of death penalty support in the United States, you'd really want to use a probability sample. Because if you're not including everybody who has attitudes about the death penalty, you might end up only looking at attitudes among one particular segment of the population. Non-probability samples, on the other hand, are often okay for estimating relationships between variables, but something to be be aware of here is still that sampling bias can affect these estimates as well. So despite the fact that non-probability samples are not ideal, they're also really, really frequently used. The reason for this is that they're often cheaper and easier than non-probability samples, or they can allow us to access populations that we simply wouldn't be able to access using a probability sample. So there are a couple of kinds that we're going to talk about. One is a convenience sample. A convenience sample is what it sounds like. It's a sample comprised of elements who were just convenient to sample at the time. For example, if you read studies in psychology, you see an awful lot of samples that are made up of college students. The reason for this isn't that college students provide any particular insight into psychological research, but rather that they're really, really easy to sample. Another example of a convenience sample would be if you went to a bus stop and handed out surveys to every person who got off the bus. So you're just going somewhere and you're sampling elements who are convenient to sample for whatever reason. Another type of non-probability sample is a purposive or judgmental sample. These are samples in which elements are selected very carefully because of their usefulness in giving insight into the population that you're looking for. Purposive or judgmental samples might be used in cases where you want to understand serial killers, for example. You can't do a probability sample of serial killers because there's no list of serial killers out there. And chances are you simply don't know a whole lot of serial killers that you could conveniently come across. But by going out of your way to select serial killers to talk to, you could come up with a sample that would give you insight into what it is to be a serial killer. But you'd be doing so very purposefully in your sampling. And so this would be a purposive or judgmental sample. Another kind of non-probability sample is something called quota sampling. And in quota sampling, you decide on different characteristics that you would like to see represented in your sample, and then you go out and you recruit enough people to fill up those quotas. So as an example, if you were trying to get a sample that was useful for understanding attitudes about something in the population, you might think of a few different population parameters like age, race, political ideology, gender, and come up with a sample that matches the United States on each of those characteristics. So if you know that the United States is 50% male, 50% female, you'd make sure that your sample was 50% male and 50% female. And whatever you got the first time, you would keep adding cases until you had filled those quotas. Quota sampling is often used in internet research, so internet panels will often keep sampling people until they've met some quota that is representative of the population on these different characteristics that you might want to see. A final kind of non-probability sample that we'll talk about is something called snowball sampling. Snowball sampling is recruiting a few people that you can find through convenience and then asking them to recruit more people for you. Snowball sampling is really useful if you're trying to understand hard-to-reach populations. So if you were trying to study prostitution, for example, it would be really, really hard to list out all the prostitutes in the United States and do a random sample of them. Just not really possible. But you could find a few people who are engaged in sex work and ask them to connect you to other people who are prostitutes, who could then connect you to other people who are prostitutes as well. And in doing so, you could collect enough members of the sample to use for a study of some kind. So snowball sampling is really, really useful if you're looking at some kind of hard-to-reach group. The difference between purposive sampling and snowball sampling is that with snowball sampling, you're relying on connections between members of your samples. With purposive sampling, you are selecting individual members of the population that you want to talk to. The last thing we're going to talk about today is sampling on the internet. And as you can imagine, a lot of research now is using sampling that's conducted on the internet. And I enjoyed this quote about internet sampling, which is that the president of the American Association of Buggy Whip Manufacturers took a strong stand against the internal combustion engine, arguing that the so-called automobile has little grounding in theory and that results can vary widely based on the particular fuel that's used. So this quote is adapted from things that have been said about internet sampling, such as that it has little grounding in theory and that the results can vary widely based on the kind of internet sample that's used. The point here, though, and this was made by a pretty famous statistician, is that internet sampling is the future, and what we really need to do is refine it and make it good, rather than just keep going on with the old ways of sampling. So there are a couple of general issues in internet sampling to consider. One is the lack of a sampling frame. As I mentioned before, a sampling frame is the list of elements in a population that you know you can reach with your sampling method. On the internet, this becomes really, really hard because no matter what kind of study you're doing, you don't actually know who has the potential to come in contact with your study. So you don't know the elements in the population that can be reached by your sampling frame. And again, you could contrast this to, say, an address-based sampling method where you could potentially list out all the addresses that could come in contact with your sampling method. Related to this is that there is considerable inequality in internet access and skills. And while a really, really large number of people tend to have internet access today, particularly through smartphones, even if they don't have computers, there is still a divergence in how much different people have access to the internet and the skills to use it. So if you're only sampling on the internet, you might be discounting the voices of people who don't have good internet access or who are not particularly tech savvy. And then finally, your spam. Anytime you sample on the internet, you're trying to get people's attention to get them into your sample, and there's a good chance that you're spam. Not true of some internet sampling methods and ways, which we're not going to go into great detail here, but there's a good chance you're spam. There are, however, advantages to internet sampling which make it a really useful tool for some kinds of research. One is that the costs are often very, very low compared to other sampling methods, but the quality stays okay. So, for example, in studies that have compared responses to surveys taken by college students and internet samples, oftentimes the people in the internet samples are paying more attention to the questions and putting more effort into their responses. So internet sampling is good if you need a really low-cost survey to do some initial research into something. Internet sampling is also good if you want to target your sample to a really specific group of people. So let's say that you're particularly interested in sampling furries from Florida who like to golf. That would be a really difficult group of people to target using most conventional methods of sampling. But thanks to the internet, it's a lot easier to get information about very sort of specific or narrow groups of people because you can find them on the internet and they often are willing to talk to you. On the internet, multiple types of stimuli are also possible, which can be helpful. In other words, you could show somebody a video or ask them to manipulate something on a screen, and otherwise do things that you couldn't do using conventional sampling methods. Finally, internet sampling can be useful in that it reduces social desirability bias. Social desirability bias refers to people giving you the answers that you want to hear. As a pretty obvious example, if you ask people if they're racist, they'll generally say no. But when people respond to surveys on the internet and they're in the privacy of their own home and nobody's listening to them or otherwise paying attention to how they're responding, oftentimes they feel more comfortable giving honest answers on surveys. So internet sampling can be useful, and because of this, it's often used in research. So all of that concludes the lecture on sampling today. So we've talked about probability samples in general. We've talked about how probability samples can be used to make good estimates of population parameters. And we've talked about non-probability samples and internet samples as well. Today's activity is going to focus on an article that I came across at one point that I thought had a truly bad reporting of statistics. And this article is How to Cope When Your Spouse is Gay, in which they say there are 2 million mixed orientation couples, and then give a whole bunch of other statistics about what happens to those couples. And these statistics were drawn from the study by Yarhouse et al. 2011 that was also assigned along with this article. And in thinking about these statistics, I want you to answer 2 questions. One is, what sample was actually used in this study? So for example, how did they get to these statistics that they're reporting in this article, like immutable facts? And so to begin with, are we looking at a probability sample or a non-probability sample? 2, considering the sampling strategy that you find, do you think the numbers reported in this article are trustworthy? And you have my opinion on the matter, but I want you to think about the sampling strategy and how that might play into interpreting the statistics that you see here. So each question on that slide can be answered with a few sentences. You really don't have to write me an essay on these. Just show that you've thought a bit about the question and made a solid effort to answer it. Always remember, these activities are graded based on effort and thoughtfulness, and I'm not grading on correctness. Responses to this activity should be posted to the discussion board by Thursday at 11:59 p.m. And comments on 2 other students' responses should be posted by Sunday at 11:59 p.m. as well. As always, feel free to reach out if you have questions, and I hope you have a great week.